Hello, podcast listeners. Thank you for downloading this. This being CrowdScience, the newest show from the BBC World Service. I'm Marnie Chesterton, I'm your presenter, and I'd like to introduce you to producer Jen. Say hello, Jen.
Hello, I'm Marnie's bossy producer.
Now, CrowdScience takes your questions each week about life, the universe, and everything in between to the four corners of the earth.
Pedant note, there are no actual corners.
Good point, thanks, Jen. In order to find answers. This week, lightning. Here's the show.
Hello, I'm John and I'm calling the CrowdScience team at the BBC World Service from Kampala in Uganda with a question. I would like to know something about electricity. Can we tap it from lightning? Is it possible to get usable electricity from a lightning strike?
Good question, John. Here at CrowdScience, your message got us wondering too. And since this show tries to answer your questions on life, Earth and the universe by heading to experts all over the world, we need to find some lightning scientists. I'm Marnie Chesterton. I can't say my name.
That's Marnie Chesterton. I'm producer Jen.
And we're on a mission to answer John's question, can we collect electricity from lightning? Where are we heading, Jen?
We're off to Wales in the UK.
And more specifically?
The city of Cardiff.
You see, lightning is a bit tricky. It's unpredictable and it's really quite dangerous to study it in the wild, as it were.
Too much for the risk assessment.
Yeah, couldn't do it. Much easier just to make your own in a lightning lab. Jen, full speed ahead to the Morgan Botty Lightning Lab in Wales.
Right you are.
Proceed 2 miles on the A303.
Jen's got a fair bit of driving to do, so let's take a moment to get some background to this topic. History klaxon! For those of you who asked about the origins of electricity when we were chatting about this on Facebook, the story of how humanity worked out that lightning is made of electricity goes something like this. One humid afternoon in the not-so-United States, this is 1752, future founding father and electricity nerd Benjamin Franklin was trying to prove that lightning was indeed electric. Yep, back then, humanity didn't know that lightning was the same as electricity. They had an inkling because early scientists, including Franklin, made sparks when they experimented with static electricity. These sparks looked like tiny bolts of lightning. As the clouds gathered, Franklin decided to test whether those tiny bolts behaved like actual lightning. He tied a metal key to a kite, grabbed his son, and headed out into the storm. Do not try this at home. This is not an acceptable father-son bonding activity. From a field on the outskirts of town, they launched the kite into the storm and held on. Franklin reported what happened next to the Pennsylvania Gazette.
And when the rain has wet the kite and twine so that it can conduct the electric fire freely, you will find it stream out plentifully from the key on the approach of your knuckle. And all the other electric experiments be performed, which are usually done by the help of a rubbed glass globe or tube, and thereby the sameness of the electric matter with that of lightning completely demonstrated.
Yeah, so that's the legend. Thing is, if Franklin had actually done this and the kite had been hit by lightning, he almost certainly would have been killed. But his proposal of the experiment was real, one among many. Here's another.
On top of some high tower or steeple, place a kind of sentry box, big enough to contain a man and an electrical stand. From the middle of the stand, let an iron rod rise upright 20 or 30 feet, pointed very sharp at the end. If the electrical stand be kept clean and dry, a man standing on it when such clouds are passing low might be electrified.
Death trap. Frenchman Thomas Francois Dalibard modified the recipe, sensibly replacing the human sacrifice with a more expendable empty wine bottle to collect the charge. He also built a taller iron rod. And lo, as a thunderstorm passed overhead, at the bottom of the electrical stand, he saw sparks. This was the first experiment to show that thunderclouds contain what we were starting to understand as electricity. But how does lightning really relate to static electricity? What actually are they both? Questions for a lightning expert.
My name is Rhys Phillips. I work in the Lightning and Electrostatics group at Airbus Group Innovations. I'm a research engineer there.
So, Rhys, I'm just wondering why my producer Jen has given me a bunch of party balloons to play with.
Well, that will be because I asked her to. So,
fair enough.
If you could take one of those balloons, are they blown up already?
No, hang on. Okay.
Now, listeners should know I'm not in the same studio as Marnie, so I can't see what's going on, but I could hear the balloon being blown up. So tie the balloon up as well.
Check.
Now, Marnie, are you within reaching distance of your producer?
Yes.
Excellent. And what sort of hair does your producer have?
Short.
That's a shame. In which case, what sort of hair do you have?
Long.
Good. OK, in that case, what I want you to do is give the balloon to Jen, and I want Jen to rub that balloon on her shirt or her top, whatever she's wearing. That balloon started off with roughly 50% positive charges and 50% negative charges. And what we're doing now is you're removing one of the charges. So let's assume you're removing the positive charges off the balloon. So the balloon has now become negatively charged. Jen, if you could now rub that balloon onto Marnie's hair and lift it up very slowly. You can tell. I think I know what's happening. I can't see you, but you can tell me what's happening.
It's coming up. That's very cool.
At this point, I'm really glad this is radio, because my hair has gone nuts. There's a whole chunk of it that's just standing on end. But normally it genuinely isn't like this. My hair, like the balloon and pretty much everything else, usually contains a balance of positive and negative charges. That's the case until you let Jen and Rhys near these things.
What's actually happening here is that the positive charges in the hair have rushed to the surface, they've attracted to the negative charge on the balloon, and just like magnets, north poles and south poles attract, with electrical charge, positive charges and negative charges attract. Now with lightning, we get this build-up of negative charge at the bottom of the cloud. The strong negative charge starts to change the properties of the air around it, and this means that that pocket of air starts to become a little bit conductive, and the same thing happens at the ground. So you've now got conductive pockets of air which are allowing charges to travel through them, negative charge trickling down from the cloud, positive charges trickling up from the ground, and if those two sets of charges touch each other, if they join up, then that closes the electrical circuit and allows a whole load of charge to move from the cloud down to the ground, and that's what we see as a lightning strike.
You have arrived at your destination. Route guidance is now finished.
Right, we are here just outside the Morgan Botti Lightning Lab. Let's see what these guys have to say about whether we can get usable electricity from a thunderbolt. So I've just walked into what looks like a big warehouse, and there are banks of batteries that are taller than I am, and there's this thing in the corner, looks like a blue shipping container, and in it is a test centre where they make a 3-inch arc of lightning.
OK, so I know it's only 3 inches of lightning as opposed to a massive natural lightning bolt, but I've taken us somewhere pretty good, no?
Yes, well done, Jen. The staff here basically get to blow stuff up with lightning, and they get paid for it, which is really nice work if you can get it. I spoke to lab manager Chris Stone to see if this was an average day in the office.
No, it's exceptional because we have the BBC here today.
You say all the right things. But
yeah,
unlike normally, do you come in and you kind of make lightning, have a cup of coffee, make some more lightning?
That's what we do. That's right, yeah. Lots of tea. We drink lots of tea. Make lightning. Have lunch, make more lightning. So, and then go home and then look forward to the next day. So,
how much do you love your job?
His job's great.
That is a man with job satisfaction. Jen, what actually is his job?
Making lightning.
Yeah, I'd got that bit. I meant, what for?
I love that it's taken you this long to ask that question. The Lightning Lab are currently testing how modern aeroplane materials stand up to lightning strikes. Cue Chris holding what looks like a bit of aeroplane, a carbon fibre copper composite panel.
This panel represents the skin of an aircraft, and on the top layer of this panel is a very fine copper mesh, which represents a metal skin, which gives you the Faraday effect on an aircraft, where the aircraft gets struck by lightning and the lightning is dissipated around the aircraft rather than going into the aircraft. The thing about carbon fibre is that current likes to go through it, and rather than go around the skin, it wants to go inside. And we don't want inside, because some of these panels are fuel tank skins.
That sounds really dangerous.
So we need to make sure that the current gets taken away.
Okay. Do planes get struck by lightning a lot?
On average, every commercial aircraft gets struck once a year.
Do you notice it if you're sitting inside?
I suppose it depends where you're sitting, really. The pilot would definitely see it. But normally they'll work their flight plan so they don't have to fly through thunderstorms.
And is it dangerous?
No, these are robustly tested. It's really safe to fly.
So future aircraft are going to be safe because of the tests that you do here in Cardiff?
I hope so.
They're not trying to harness lightning here. We've not forgotten John's question, but they do make thunderbolts, and we got to see how and where they do, in that big blue box that looks a bit like a shipping container. And that's where the magic happens.
So in the corner of the big blue box, we've got a test rig, which is probably 2 metres high.
It looks like two kitchen tables kind of stacked on top of each other.
It's stacked on top of each other, yeah, that's right, with plastic legs.
And this is actually where you make the lightning.
So, yeah, this is where we make the lightning. Outside the shipping container, there are various bits of equipment that represent, say, clouds and the charging mechanism within a cloud for creating lightning.
So when you fire this thing, where are you? Where should we be?
As far away as possible. We've got another box that we sit in away from this box, which keeps us protected.
Right, well, let's make some lightning. Is that all right?
That's fine, yeah. I'll set it up and we'll go from there.
While the system warmed up, we put in some ear defenders and headed for safety, away from the lightning test rig to a second, smaller, not blue box.
In our little container, which we call our control room, we set the voltages that we charge our batteries, capacitors to, and then we press a little green button which makes the lightning.
Can I press the button?
You can.
Excellent.
Now we're ready to fire.
Okay. You ready?
You got your earplugs in?
3, 2, 1.
Fire. Woo! That's lightning, Jen. I pushed a button and made lightning.
I know that makes you very happy, Ronnie.
I just think that's really impressive. Can we hear that again? And what had that tiny lightning bolt done to the aircraft panel?
So what you'll smell in the test chamber is the smoke or the fumes that are created after a strike. And you can see it as a faint haze in the top of the test chamber.
Oh, yeah.
And you can smell a
Burnt
slight
aeroplane.
burnt carbon fibre smell. Burnt aeroplane.
And the test panel itself has a big black splodge.
Yep. Although it's a nice big black splodge, it's not a very deep big black splodge because all the current has gone through the copper mesh. So this has worked very well.
So this kind of strike happens to aeroplanes once or twice a year. But back to John's question. And if these guys in the lab make lightning, they presumably know how to direct and harness the stuff. I asked Chris. OK, so you work with lightning a lot. What do you think about listener John's question? Can we get usable electricity from lightning?
Well, I'm not going to say no, but it's very difficult.
What? I think that's a very negative attitude. I mean, they managed to make their man-made lightning come out of the same place day in, day out. Is the stuff in the wild really that different?
The thing with lightning is that it's very sporadic. You can't predict where it's going to strike. Thunderstorms are everywhere, and a lot of the energy in a lightning strike is taken up by the actual strike itself, so light, sound, heat. So the recovery of power at ground level is very small.
Uh-oh, this does not sound good. Back to Reese. What does he reckon about the chances of harnessing power from a lightning strike?
Well, do you want the long version or the short version?
How long is the long version?
Well, the short version is no.
I'd like the long version, please.
Okay, well, I get asked this question a lot, and I used to tell people, no, we can't do it because we just don't have the technology to do it. After a while, I figured that as an engineer, that's a pretty rubbish answer, because the job of an engineer is to try and create the technology to do things. I sat down with a friend of mine, Phil Leisher, and Phil actually built the Lightning Laboratory. Between us, we've come up with some numbers. First of all, there's roughly 500 megajoules of energy in a lightning bolt. Now, most of that gets lost in the heat from the lightning, the sound of the thunder, and the light that you see, of course. Let's assume that we can gather 10% of the lightning from the bolt. So that's 50 megajoules of energy, which happens to be enough to boil about 150 kettles. Now, I was looking at what this would mean across the world, and the world gets struck by lightning about 44 times a second. Now, obviously, some parts of the world get struck more, some less, but for this, I'm just assuming it's a sort of an average that everywhere's getting struck roughly the same. So 44 times a second is about 1.4 billion times a year, which would create 70 billion cups of tea.
Brilliant. That's almost enough for me.
So how much would it cost to do this? Well, to actually be able to collect this lightning, we need some pretty serious infrastructure. We'd need a network of collecting towers. Probably each tower would have to be about half a kilometre high, and these would be big metal structures with huge capacitors on the top and some overvoltage protection. And we reckon that each of those towers would cost about £20 million in British money. And I did a quick calculation, and I think that means to cover the world in enough to collect these things, you need to spend about $12 quadrillion. That's 12 with 15 zeros after it.
Is that more money than we have in the world?
It is. The world's got approximately $241 trillion US, so that's about 50 times more than the total amount of money in the world to be able to collect lightning.
Even building those tall collecting towers is no guarantee of catching any lightning. We had another question from listener Sharon in Florida.
Hi, CrowdScience. I am Sharon, and I'm calling from Windermere, Florida. I would like to know, is there any way to attract lightning? Thanks.
No, not really. It does depend on what scale we're talking about. Talking about things on the ground, for example, tall objects will get struck, but you're not really attracting the lightning. The lightning is close by, and at one of those junctions where it's deciding which direction to jump in a zigzag position, it's looking for something that's conductive, for example. And so at that point, if you're within a few feet, you might be able to influence where it's going to jump to. But in terms of if you're trying to attract lightning down to a tower or a house or a building of some sort, then I don't really think you're going to have much success in really attracting lightning down in that sense.
OK, so John, it seems that a global network of lightning catchers is not looking likely at this point. Everyone we asked is telling us that it's both very difficult and unbelievably expensive. But here on CrowdScience, on the BBC World Service, we don't give up that easily, or rather, producer Jen doesn't. Jen, where do we go from here?
I think we need to think about this more from John's point of view.
What do you mean?
Well, exactly that. I mean, why might he have asked that question?
I don't know. Does he see a lot of lightning in Kampala?
I have no idea, but I know a woman who might do. Professor Rachel Albrecht. Rachel, it's Jen and Marnie. Can you hear me?
Yes, I can.
Brilliant. Oh, hello. How are you?
Hi, good.
That's my line.
Sorry.
Hello, I'm Marnie. How are you, Rachel?
I'm fine, thank you.
I'm sorry for calling you so early in the morning.
That's not that early.
Tell me a bit about what you do.
I am a meteorologist, and now I am a professor at the Department of Atmospheric Sciences at the University of São Paulo. Basically, we look at thunderstorms from satellites. So the satellite sees the top of the storms and how the lightning illuminates the top of the storm. So then we can count where most lightning is happening in the world.
So you've got this global picture. Well, we've got a programme that's all about lightning because our listener John asked us if we could get usable electricity from it. So we want to know things from his point of view, and he lives in Kampala. So how much lightning is there in Kampala? Is that something your satellites have picked up?
Oh, yeah. Kampala is definitely around the hotspots. It's not a hotspot itself, but it is very close to Lake Victoria, where we have a lot of lightning.
And how does that compare to, say, London, where I am?
Oh, London doesn't have much lightning. London has a lot of rain, but not much. If you count like the whole city, it would be around 6,000 lightning a year over London. While over Kampala, which is like a very small town, we have 4 times more lightning than London there.
4 times?
Yeah.
So, wow, Kampala gets a lot of lightning, and it's situated on the north shore of Lake Victoria. Is that a coincidence? Are lakes particularly hot spots?
No, it's not a coincidence. Most of the big lakes in the tropics, they have a lot of lightning on them. The place where we have more lightning in the world is Lake Maracaibo in Venezuela. Lake Maracaibo have similar features as Lake Victoria because it is a round lake in the tropics, so it also has nocturnal thunderstorms over the lake, the same mechanisms with convergence of wind breezes over this warm lake during the night. But Lake Maracaibo also has mountain valley breezes during the night that gets this convergence stronger. So over the whole lake, it is like 3 million lightning flashes in the year. But pay attention that the lake is big. Okay, it's like London. It's not. London is like 10 times smaller than this lake.
Rachel, that's great. Thank you. We've got to make the rest of the programme now, so we've got to go. Bye!
Bye!
OK, so now what?
All right, so instead of a global network, which, as we've been told, is in no way cost-effective.
The one that would cost more money than there is on the Earth?
Yes, that one. Instead, what if we put a small network of these lightning catchers in these lightning hotspots and then transmit the energy to where people need it?
I love how you're not giving up on this.
Nope.
We need an expert in both power transmission and lightning. Handily, and perhaps unsurprisingly, there is one at the Lightning Lab.
I'm Professor Mann. I work at Cardiff University and I'm the director of the High Voltage Research Group, and I research in high voltage systems, including aircraft.
You're not originally from Cardiff, are you?
No, originally I come from Algeria.
Lots of lightning in Algeria?
Yes, I come from the mountainous region of Kabylia, which is east of Algiers, and it's full of lightning.
Wow, I didn't know that. So we found out that a global network of lightning catchers isn't really viable. What if we just put a few in the most struck places on Earth? How about if we just kind of localised the collection points to those areas? Is that going to be useful?
I think it'll be very hard to make any use of that sort of network because, first of all, you can't predict where lightning is going to strike on the ground. Even if you have a lot of antennas or receiving networks, you may not get the lightning strike to it. It could actually strike next to it, maybe 100 meters, 200 meters away. So that's one aspect. The second one is the amount of energy or charge that is transferred from the cloud through this lightning strike. It's actually very little energy.
Now, we asked Manu about this a bunch of different ways because Jen made me. But at every turn, the answer was pretty definitive.
In terms of power, we can transmit over very long distances. But with regards to lightning, the amount that you will capture from a single strike is so small that it's not even worth thinking of sending it anywhere.
But one thing he said gave me hope.
In Florida, there is a station where they do triggered lightning. They launch rockets to the cloud, and then that creates a lightning strike to a specific point on the ground.
Really? What are they doing that for?
That is to study the lightning phenomenon and also to look at various aspects of lightning.
OK. I'm not sure where I go from there.
I know exactly where you were going from here. Straight to YouTube to look at videos of scientists catching lightning with rockets.
It was for work, basically, yeah.
All right, so why did this mention of triggered lightning give you hope?
Because it sounds like we don't know everything there is to know about lightning yet. I mean, some of the stuff Rhys Phillips told me was frankly nuts. And I asked him some fairly random questions because, well, you know, assume nothing when you're talking to a lightning expert. And the most bonkers answer was this to my question, does lightning always come from the cloud to the ground?
Actually, no. It can go the other way. It can start at the ground and go up to the clouds. But actually,
What?
yeah, it's a very similar process that takes place. It's just sort of in reverse. But actually, 90% of lightning strikes are not involving the ground at all. They're purely up in the sky, so it's charge that moves from one bit of a cloud to another cloud or between two different clouds, for example. So they don't actually come down to the ground at all.
Do we properly understand lightning at all?
In terms of fully understanding the nature aspect and how it forms, then we definitely don't fully understand that. And there are researchers around the world who are doing research from a natural point of view, trying to understand things like that. As an engineer, we don't need to fully understand how it forms in order to protect our planes against it. So it's kind of not the important, as much as it's fascinating, it's not the important aspect for us.
All right, I'm glad that the engineers are getting on with protecting us from this stuff, but I don't get why humanity's ignorance about lightning gives you hope.
It means that despite everything we've heard today, I've still got scope to give a glass half full answer to John's question, can we tap electricity from lightning? Well, John, not now we can't, but in the future, maybe.
We never say no, but at the moment, what we know and what we have, I think it's almost impossible right now. But in future, who knows? Maybe we can gather all the charges in the clouds and put them in one bucket, and maybe you can use it.
That is it for this edition of CrowdScience on the BBC World Service. Today's big question was from me, John Emocho in Uganda. The program was presented by Manny Chesterton and produced by Jenny Winty. If you have a question about life, art or the universe, please email it to crowdscience@bbc.co.uk. Thanks for listening. Bye.
Hey pod people, that was CrowdScience. Thank you for listening. One thing that we're hoping that the CrowdScience podcast listeners could kind of help us with in a sort of crowdsourcing way. We've been arguing all week in the office about Benjamin Franklin's accent. Obviously, we got hung up on the important detail, right, Jen?
Absolutely.
So I think it would have been nice to have him as an American. I mean, he's American, right?
He's known as the first American, but of course this is the 1700s, and Franklin's father had come over from England. Many other people in Boston, where Franklin grew up, were English immigrants. So you have to then ask, what would anyone's accent, either in England or America, have sounded like at that point?
Right, and we don't have any records of that, and there's no proof that we didn't all speak with American accents. But if any of you have strong views, let us know what that's based on. Jen loves reading ranty emails, so send them to crowdscience@bbc.co.uk. We may even put your answers in a future edition of this very podcast. Oh, and also don't forget to send us your science questions. Bye for now.